Hello, so this is part 2 of our lecture series. So now we will actually sort of try to incorporate the Euclidean commute time distance into K-means algorithm, and we will set it up as a Markov chain. So remember, the intuition here is that on the right hand side you see there's a figure, right? The Euclidean commute time distance has the property that if there are many connections between two nodes, then the distance for those two nodes should be small, right? For instance, in this case, between I and K, the distance should be relatively small because it has a ton of connections, right? And the distance between I and L should also be relatively small because they are physically closer to each other. So for cases like these, I hope the intuition is clear that clustering would make clustering easier. And so we will begin setting up our Markov chain. Okay. So first we will consider a weighted graph, weighted and connected graph. Okay, so connected just means every single node can be reached from any other node, right? And the weight means that every single one of these edge over here, there is a weight on for this edge, and for every of these edge there is some kind of weight. Well, this is an L. Whoops, sorry about that. And so in this case we require that the weight ij between two nodes to be symmetric, okay, and that these weights are sort of sensible in the sense that it is greater than 0, so there's like no negative weight. Okay, what is our Markov chain? Every single node is a state in a Markov chain. Okay, so in order to specify this Markov chain, we need to specify the transition probability. Okay, we are going to say the probability to go from node I to node j. We will denote this easier notation using just p subscript ij, and the probability is just going to be equal to the weight for ij divided by this out of the total outgoing weight. Okay, so let's just say wik. So out of the total possible number of ways to leave I, what is the edge weight to go to j? That will be the probability of ij. So this probability for every node sums to 1, and it makes sense. So what this means is that high weight, high wij, is equal to easier communication. Okay, well, it's easier communication. Okay, so a few. I will also say that the fact that we have connectivity here, right? Let me put on a highlighter, connected graph. Because the graph is connected, the Markov chain is irreducible, right? So if you don't remember what this means, it just means every state can be reached from every other state, right? Reachability, something like that. And finally, we want to say that each step, the chain must move. So what this means is that you can't stay at the same state after one step. This is like a random walk. Every time you walk somewhere, you have to like actually move somewhere. Okay, so this is a Markov chain. So you can think of this. There's a person over here, and then at each step he can move this way, that way, or that way, and well, my art is like really good. Anyways. Based on this Markov chain, right, we will define two important quantities that we are going to use very often, and they will be the basis for what is our commute time distance. Okay, the first one is starting at node I, the average first passage time. Average first passage time. What is this? Is defined as the number of steps a random walker needs to enter state K. Number steps is the average number of steps needed to enter state K, to enter K. Okay, so in notations, what do we have? We have conditional on that the current state is I, right? I want to move to K. So what is this equal to? This is the notation. And we have a Markov chain, right? We can think about this intuitively. You are at Y. So the first step is you need to leave your state and go to some other state, right? So either this way, or some other way. So you can go to some other state. Let's call it J, right? And doing that will give you one. You took one step, right? And then after you went to J, you have to go to K from J, right? And that is what is the average number of steps to do that is exactly captured by our function m, right? So now you want to go to K starting from state J, okay? And what is J? J sums over every single value. Well, that's an ugly J. Let me see. How do I erase? Oh. Okay. All the possible neighbors of I, you go to J, and then you won't go from J to K. Okay, and but the base case would just be if you are already at K, then the number of steps to go to K is 0. Okay, I hope this is pretty intuitive. And the average first passage time. Okay, this is a very important quantity. Okay, and then there's another very important quantity. The same thing. Starting at I. The what is this one? Average commute time. Average commute time. So this is like, going to work, you're starting at I, you go to work at J, and then you come back. Okay, that's why it's called average commute time. Is equal to is the average number of steps to enter J, then go back to I, then back to I. Okay, so we denote that by the quantity n. Okay, so you want to go to conditional on that you are at I, you want to go to J for the first time and then go back to I. Okay, and based on the average first passage time, you can basically write that in terms of m, right? So you are at I, you want to go to J, and then you are at J now, you want to go to I. So I hope these two quantities are pretty intuitive. So what is n? Okay, first of all, you can observe that n is symmetric, right? Just because you're adding up two terms that is just symmetric. So n is symmetric, and in fact you can show that n is a metric. So in fact it satisfies the triangle inequality and all of those propositions. And you can for a proof of this, you can just go to my notes, and then there would be a reference to y. But it is important to go over into intuition for I. Okay, let me just say this: intuition. So I guess there's two very important intuition, right? If J is close, then because our weight is symmetric and everything, then going to J and then coming back is going to be small, right? Nji small, right? But at the same time, if J highly connected to I, then that distance will be small too, right? Because there's many different communication between I and j is also small. So what do we get? Then nji small as well. Okay. So this is why we have that n, the quantity nji. This is very important, okay? Is well, actually that's the square root of it for some more complicated reason. But this quantity is actually called the Euclidean commute time distance, okay? Euclidean commute time distance. Okay, this is, let me just put that in highlighter. Okay. Wow, perfect. And so the fact that it takes connectivity into account is sort of crucial, right? It's the thing that sets apart from other things like shortest path, Dijkstra's distance, that kind of stuff, because connectivity is crucial. And we will move on to the next video for an introduction for how to compute this.